Okay, so welcome to the fifth talk of Istanbul Observatory. Today we have a speaker from Christ University, Neal Titus Thomas, and he's working on soft X-ray transit, and today he will give a talk on soft X-ray transit, spectral properties of a soft X-ray transient, MAXI J0637-430. So Niels, you can share your screen and you can start.
All right. Thank you. Right. Is my screen visible?
Yes, perfect.
All right. So a very good afternoon to everyone. Before I begin, I'd like to thank the Istanbul University for inviting me to share my research with all of you. It is an honor to be presenting my research at a university of such rich heritage and renown. And so with that, I'll start with my talk. The title of my talk is Spectral Properties of Soft X-ray Transient MAXI J0637-430 using Astrosat. So this is going to be the outline of the talk. I'll first give a brief introduction on X-ray binaries, followed by the Astrosat mission. And then I'll talk about the source, MAXI J0637-430, and then the spectral studies of the source using Astrosat, followed by the results and discussion. All right, so X-ray binaries. X-ray binaries are systems consisting of a main sequence star and a post-main sequence star in a compact and a compact object, which may either be a neutron star or a black hole in a gravitationally bound binary orbit. This is what an X-ray binary looks like generally. So you have a compact object here at the center, which may either be a black hole or a neutron star. And you have a companion star which goes around. And as time goes by, the matter from the companion star is spilled into either into or onto the compact object. Now, these systems are luminous in X-rays, and they are produced due to the transfer of matter from the donor star onto the compact object by means of an accretion disk due to either Roche lobe overflow or due to stellar wind. Of these two mechanisms, we are more interested in the Roche lobe overflow, as you would find out later on. So I'll just give an idea of what a Roche lobe overflow is. So what happens is matter, usually from the compact object, it goes past the inner Lagrangian point, that is the L1 point, and it spills onto the compact object. Now, due to the conservation of angular momentum, the matter forms a flattened accretion disk, and the viscous stresses heats the material to 1,000,000 degrees, and then what happens is the disk radiates in primarily X-rays. So this is what accretion via Roche lobe overflow looks like. Here you see the compact object. Here in this case, it's a neutron star, and you have a companion star, and you see matter spilling past the inner Lagrangian point, forming an accretion disk, which radiates X-rays. Now, on the other hand, we also have accretion via stellar wind, where matter is accreted not via an accretion disk, but it just has these very violent wind outflows, and it gets funneled onto the compact object by various processes. Now, in addition to the accretion disk, there is also an emission of X-rays from an extremely hot region in the vicinity of the compact object. And this region is called the corona. Together with the accretion disk and the corona, you have X-ray radiation, which is dominated by either one of these sources, or it's a combination of all these X-ray processes. So you have black body radiation, you have thermal bremsstrahlung, inverse Compton scattering, synchrotron radiation, and the FEK fluorescence. This here is the schematic of what an X-ray binary looks like, and the different components of an X-ray binary. You see an accretion disk here, and the emission that comes from the accretion disk is usually black body radiation or thermal bremsstrahlung. And then you have the Comptonized region, which is the corona, which is around the compact object. And then sometimes what happens is the radiation from the Comptonized region gets reflected off the X-ray of the accretion disk, and you have a reflection spectra that is exhibited by the source. And this reflection spectra appears to be in the form of K-X-ray fluorescence. So if we were to get the spectra of the source, what would happen is we would see different components of the X-ray binary exhibited by different X-ray processes. So you have the black body radiation, which looks like this. It peaks at lower energy. And you have the Comptonized emission, which peaks here at higher energies. And then you have the K-X-ray fluorescence, which in this case, usually it's ion fluorescence, which peaks at 6.4 keV. So you see an ion peak here. Now, based on the mass of the companion star, X-ray binaries are categorized into low mass X-ray binaries and high mass X-ray binaries. Low mass X-ray binaries usually have a donor star, which is G, K, or M type star, and has a companion mass of 1 to 2 solar masses. And high mass X-ray binaries has a donor star of O, which is usually O or B type, and has a companion mass of 5 to 20 solar masses. Together, X-ray binaries, both low mass and high mass, exhibit a range of spectral and temporal properties, which help us understand the nature of the central compact object. Because the radiation that comes from these systems are influenced by the relativistic effects around the compact object. So by studying the radiation of the accretion disk, coming from the accretion disk, you can infer some properties of the central compact object. And probing these systems would shed light on the X-ray emission variability and provide a platform to study matter and energy cycling under extreme conditions. So there's a subclass of X-ray transients called subclass of low mass X-ray binaries called soft X-ray transients. Now, what are these? These systems are extremely faint sources having luminosity between 10 power 30 to 10 power 33 ergs per second during most of their lifetime. And they are characterized by a non-steady transfer of mass onto the compact object. For the most part, they go undetected. For most of their lifetimes, they go undetected. But sometimes they undergo sporadic outbursts, and these outbursts occur at intervals of 1 to 60 years. And during these outbursts, what happens is the X-ray luminosity of these sources increases by a factor of 10 power 7. And then it decays back into quiescence. Now, the decaying happens at an e-folding time scale of 30 days. And during these outbursts, these sources appear as one of the brightest X-ray sources in the sky. Okay. I'm so sorry, I made a mistake here. This should be 10 power 37 to 10 power 38. Now, the occurrence of these outbursts is attributed to instabilities in the accretion disk that are both viscous and thermal in nature. This is an image of an X-ray transient that is GX339-4. It consists of a black hole as the central compact object. You see how the luminosity peaks and then decays over several days, and then it goes back into quiescence where it has little to no activity, and then after several years or months, it goes into another outburst, and which again decays, and so on and so forth. So it follows this outburst cycle. What is interesting is that some sources have a very quasi-periodic outburst cycle. So it goes under outbursts every 2 to 3 years. But then there are some very peculiar sources which do not have any sort of periodicity when it comes to their outburst cycle. They're just very, very sporadic. Now, the X-ray spectra of low mass X-ray binaries consists of two components. One is the soft component, one is the hard component. The soft component is under 10 keV, and the harder comptonized component dominates over 10 keV. Based on the relative luminosity, the total luminosity and the relative contribution of these two components in the spectra of X-ray binaries, one can distinguish several spectral states of the source. There are two major spectral states of X-ray binaries. One is the high soft state. High here indicates high luminosity, and the other one is the low hard state. Low, where low indicates the low luminosity. So in the high soft state, what happens is the spectra is dominated by thermal emission, which is probably from the optically thick accretion disk. And it has a very weak hard power law that is observed. The high soft state has a photon index of greater than 2. On the other hand, you have the low hard state where the spectra is dominated by the comptonized emission from the corona, and it has a hard power law having a photon index of less than 2. So what do these high soft and low soft state actually mean? It's nothing but the accretion geometry, two different modes of the accretion geometry of these X-ray binary sources. So in the high soft state, what happens is you have your accretion disk, which comes very close to the compact object, which gives very little room for the corona to grow. And most of the accretion, most of the radiation that you see from the source is dominated by the accretion disk. This is also characterized by an increased mass accretion rate. Now, on the other hand, you have the hard state where the accretion disk is truncated at a very large distance from the central compact object, and you have a lot of space between the compact object and the accretion disk for the corona to grow and to be present. And in this case, the radiation from the source is dominated by the comptonized corona rather than the accretion disk. Now, when you get the spectra of these two states, you see a very marked distinction between them. In the low hard state, here you see the spectral states of this black hole source called Cygnus X1. You see in the hard state, the spectra is dominated by comptonized emission, which is indicated here by this blue line. And in the soft state, the spectra is dominated by the disk, and which is indicated here by this red line. So you have two distinct spectra. I mean, the two states of X-ray binaries translate into two very different looking spectra of these systems. So in order to study these sources, to study these X-ray binary sources, the Indian Space Research Organization launched an X-ray observatory mission called Astrosat. Astrosat is India's first dedicated astronomy mission aimed at studying celestial sources in X-ray, optical, and the ultraviolet bands simultaneously. Astrosat was launched on September 28, 2015, and its main objectives are to understand high energy X-ray, high energy processes in X-ray binary systems consisting of neutron stars and black holes, estimating the magnetic field of neutron stars, the study of star birth regions and high energy processes in star systems that lie beyond our galaxy, to detect new X-ray sources, much like the one I'm going to talk about later on, and to perform a deep field survey of the universe in the UV band. So Astrosat carries a total of 6 experiments or payloads, which start from the ultraviolet region here. So that is the UVIT. It's the ultraviolet imaging telescope. Then you have the soft X-ray telescope, SXT, and the large area X-ray proportional counter, LAX-PC. Then we have the cadmium zinc telluride imager and the scanning sky monitor. CPM here is the charge particle monitor. We do not really do any science with it. For the most part, for X-ray binaries, the instruments that we use to study is the soft X-ray telescope and the large area X-ray proportional counter. I'm going to give you a brief rundown of these two instruments before we talk about the actual source. So this is the soft X-ray telescope. It is a grazing incidence doubly reflecting X-ray focusing telescope, which is cooled by a charge coupled device. Its operating range is between 0.3 to 8 keV, and it has a spatial resolution of 2 arc-minutes. SXT detects photons with a spectral resolution of 150 electron volts at 6 keV, and has geometric area of 250 centimeters square. The temporal resolution of SXT is 2.337 seconds. So it's not very good when it comes to resolving temporal features of sources. For that, we use the LAX-PC instrument. Now, the SXT telescope was developed by the Tata Institute of Fundamental Research in India, and the focal plane camera and the charge coupled device was from the University of Leicester in UK. Then we have the LAX-PC. It is 3 proportional counter arrays, which operate in the energy range 3 to 80 keV. The very important and very significant feature of LAX-PC is that it can measure X-ray photons at very short time scales. So we can do some really good temporal studies down to 10 microseconds. And it has a spectral resolution of 9% at 22 keV. And the geometric area of LAX-PC is very large. It's about 10,000 centimeters squared. This again was developed by TIFR in Mumbai. This is just a brief rundown of all the parameters of the different instruments. So you see As I mentioned, LAC-SPC has some excellent temporal capability and has very large effective area. And both together, LAC-SPC and SXT is able to detect and study X-ray sources from 0.3 to 80 keV. Now, the very significant part of the Astrosat mission is that LAC-SPC and SXT together are able to give you simultaneous data. So that is something that has been missing in erstwhile missions. So you have the RXTE mission, which operated from about 3 to 30 keV, and we were missing out on a lot of data under 3 keV. But LAC-SPC remedies that problem by having two instruments, one in the very soft region and one in the hard region, look at sources together so that we can correlate the information that we get from both instruments and get a better picture of the source. So now let's talk about the source itself, MAXI J0637-430. This source was first detected by the MAXI NOAA alert system from 2nd to 3rd November 2019 in 2 to 4 keV and 4 to 10 keV bands. The X-ray spectrum was modeled with an absorbed black body and a power law, and the spectral fit yielded an inner disk temperature of 9 keV and a power law index of 2.3. There was an optical counterpart that was detected with a brightness of view 14 in the Vega band by the Swift view watt, and the position at which this optical counterpart was detected was not consistent with any other known star's position, and that is why it was deemed that this source, it was the detection was the optical counterpart of the source, and it has undergone a significant brightening, as is common in the optical counterparts of black hole sources in low mass X-ray binaries. These results are published as an astronomer's telegram by Kiana et al. In 2019. This source was also observed in the radio band with ATCA, having flux densities of 66 microjansky at 5.5 gigahertz and 60 microjansky at 9 gigahertz. Now, apart from this, there were a lot of other missions. There was some nicer observations too, and I think there was New Star and XNM Newton too, which observed this source. So, encouraged by this, we made target of opportunity observations of MAXI J0637-430 using the soft X-ray telescope and the large area X-ray proportional counter to study the source in the 0.3 to 80 keV energy band. We made two observations. Here you see the observation log dated 8/11/2019 and 21/11/2019 for the exposure times mentioned here. So coming to the spectral studies of MAXI source with Astrosat. So this is where we made the observation. This is the plot of, this is the MAXI light curve, one day bin MAXI light curve in the 2 to 20 keV band. And you see that we have observed these, we have made our observations at two different points during the outburst decay, one at the very beginning and the other one a little later. So we used standard SXT and LAC-SPC pipelines to reduce the data, to clean it of dropouts. And then the first step was to generate light curves to see what the light curve looks like and if the source shows any variability. Unfortunately for us, the light curves did not show a lot of variability. So on the left panel here, you see this, the purple color plot. The first panel shows the SXT light curve from 0.7 to 7 keV. The second panel and the third panel are LAX-PC light curves in in 4 to 5 keV and 5 to 30 keV. And the last panel is the ratio of these two counts. So in observation 1, you see that you have two distinct clumps of data, and the second the second clump of data shows a brightening. I mean, that shows an increase in flux, which translates to the two LAX-PC, which translates in the two LAX-PC light curves and also the hardness ratio here. The second observation on the right side shows the source to be the flux to be more or less constant in the SXT light curve, which is the first panel from 0.7 to 7 keV. In the LAX-PC light curve, we see the flux to decrease as the observation progresses, and the hardness ratio looks more or less constant. So normally when we study these sources, what we do is we try to find the spectral parameters of the source as a function of time. But because we did not have, the source did not vary too much as a function of time, instead of doing time-resolved spectroscopy, we decided to do something called the flux-resolved spectroscopy, which is done by generating the hardness intensity diagram. So what are the hardness intensity diagram? It's basically, first you get light curves of the source in two energy bands. And on the x-axis, you plot the total intensity of both the light curves, and on the y-axis you plot the ratio, that is the hardness ratio, which for LAX-PC 20 data, we define the hardness ratio as the ratio of counts from 5 to 30 keV by counts in 4 to 5 keV, and intensity was defined as the counts in 4 to 30 keV. Now the HID of the LAX-PC data showed 3 distinct regions. And because of that, it was not possible to determine if the source showed characteristics of the Q diagram that is exhibited by black hole Lomas X-ray binaries, or the Z or Ertl pattern exhibited by neutron star Lomas X-ray binaries. Now, in order to study the hardness intensity diagrams in energy ranges that is lower than 4 keV, we generated a 50-second binned HID with the SXT data, with the hardness ratio defined as the ratio of counts in 1 to 7 keV by 0.3 to 1 keV, and the intensity defined as counts in 3 to 7 keV, which unfortunately did not show any distinct regions. So this is what the HID for LAX-PC data looks like. You see observation 1 is plotted in a purple color. You see 2 distinct regions in observation 1. And observation 3 shows this one big clump of data. Observation 2 shows one clump of data, which was deemed as a region 3. Now this is the HID for the SXT data. It does not show any distinct regions. All of it is just clumped together in this big blob. So there was not much we can do. We could do with. We could not perform flux-resolved spectroscopy resolving the source in SXT HID. So instead of that, what we did was we used the LAX-PC HID, and we got the spectra, the simultaneous spectra for SXT and LAX-PC together for these 3 regions to study the spectral parameters of the source. So simultaneous data were generated for both SXT and LAX-PC, and we did a combined spectral fit in the energy range of 0.5 to 5 keV for SXT because above 5 kV there were some dropouts, and under 0.5 kV there was a lot of noise. And for lax PC, we generated the spectra, or we fit the spectra between 4 to 20 kV, as the background about 20 kV was very high. And we fit the spectra with the model combination TB-ABS, simple, disk BB, and the Gaussian. TB-ABS here takes care of the absorption of the X-rays that comes to us by the interstellar medium. Simple is a convolution model which takes care of the Comptonized region of the source. Then you have disk BB, which is the multi-color black body model. And then we have the Gaussian, which takes care of the X-ray fluorescence line that we saw at 6.4 kV. Now, this is the best fit parameter of the flux resolved spectroscopy. Now, what is to be noted here is that the disk BB temperature, KT in, for all the three regions was around 0.6 keV. So for region 1, it's 0.61 keV, for region 2, it's 0.65, and for region 3 is 0.52, which indicates a cool accretion disk. Also, what is to be noted is that the photon index of the simple model is either 2, it's either close to 2 or above 2, which indicates the source to be in the soft spectral state. There were residuals at 6.4 kV, which made it necessary for us to include a Gaussian model and freeze the value at 6.4 kV. And for all the for all the fits that we did in all the three regions, the reduced chi-square was pretty good. It was close to 1. Now, if you see here, the norm of the disk BB varies from 1455 to 2103, but this is more or less constant. Right? So we had a constant. This variation is not very significant, and we can say that it is constant. So if the norm is constant, so the norm here is a proxy for the inner disk radius. So if the norm here is constant, it translates to the inner disk radius being constant. And if the inner disk radius is constant, then in order to substantiate, in order to take that out of the equation, what we did was we got the average value of these three regions. We found it to be 2075, and we froze the model, the norm of the model to 2075, and we refit the data. So just a second. Yeah, so we froze it to 2075. So when after doing that, we also calculated the unabsorbed disk flux and the total disk flux, and we got the ratio of the unabsorbed disk flux and the unabsorbed total flux. And the ratio was seen to be close to 9 in all three regions, which means that most of the emission that we observed from the source is dominated by the accretion disk, which in turn points that the accretion, that the source is in the soft state. I have some images of what the spectra looks like for all the three regions. You have region 1 here on the left side, region 2 here on the right side, and region 3 at the bottom. Yeah, that's that. Now coming to the results and discussion. The accretion disk temperatures of 0.61, 0.65, and 5.2 in the three regions respectively point to a cool accretion disk. and the slightly lower value of the disk temperature, that is 0.52 in region 3, correlates to the disk being harder in the HID. So if you remember the HID, you see region 3 is harder, and that is why the temperature is lower. The disk temperature is lower in region 3. The disk BB norms of 2103, 1455, and 2083 in the 3 regions indicate a constant accretion disk. And this observation is consistent with many black hole low mass X-ray binaries in their soft state, because they too have a constant accretion disk. Now we made some assumptions that the source distance is 10 kiloparsecs and the inclination angle is 70 degrees. And with this assumption, we calculated the inner disk radius to be 98, 81, and 97 kilometers in regions 1, 2, and 3. For that, we use the relation norm, that is the disk BB norm is equals to Rn by d10 square cos theta, where d10 is the Rn is the distance of the radius of the inner accretion disk. D10 is the distance to the source in 10 kiloparsecs, and theta here is the angle of inclination. Now, for a black hole of mass 20 solar masses, keeping the disk normalization at a constant at 2075, we estimated the inner disk radius to be 6 Rg. Now, this is the distance at which the innermost stable circular orbit is located for a non-rotating black hole. In addition to this, the presence of the Gaussian line at 6.4 keV, which is due to the reflection from the accretion disk, shows a width of close to 1 keV in regions 1 and 2. Now, a width that wide shows that this emission feature is broadened due to the relativistic effects around the vicinity of the compact object. Like I said, the ratio of the unabsorbed disk flux to the total flux is close to 9, which suggests that the accretion disk, the source is disk dominated. And this, along with the fact that the power law index is greater than 2 across all the regions, shows the source to be in the soft state. So the conclusion of our study is that MAXI J0637-430 is a strong black hole X-ray binary candidate, considering all its spectral parameters. Apart from that, we also performed some temporal studies, but unfortunately, we could not really get any temporal signatures from the source. Right. So that's about it. This work has been published as spectral properties of soft X-ray transient MAXI J0637 using Astrosat in the Astrophysical Journal. And these are the co-authors of the paper. I would also like to take this a moment to mention that I'm from a research group here at Christ University, and we primarily work on X-ray data from X-ray binaries, black holes and neutron stars, and we primarily work with the Astrosat mission in conjunction with the SWIFT, NICER, New Star, and XMM Newton 2, and we are open to collaboration. So if your research interest lies or aligns with what we do, then kindly write to me and we can collaborate and come up with some work together. Thank you.
We thank you, Neal.
Did I overshoot the time, or was I?
No, that was perfect. And actually, I also personally thank you for a very instructive talk. it was, I'm sure it was very helpful for our student as well, especially the introductory part on X-ray binaries. So thank you for that. If there is any question from the audience, we are happy to take them. Is there any question? So, yeah, Şölen, it's your turn.
Is someone asking me something? I can't hear.
Yes, Şölen Hoca will talk now.
Sorry, now you can hear me?
Yes,
Okay.
yes.
Okay.
I can.
And also we can see you. Good.
Okay, see me and hear me. Okay, excellent. I end up asking the questions, so somehow I have a very quick question actually. Not can you go back to the spectra when you saw the show the in region 1, 2, 3 spectra? Here. I noticed that hold on, I have a slight problem here. Okay, all right. And in here in the region 3 here, your residuals fluctuate so much. Why? That's a 4 sigma variation there.
Yeah. So
is that sigma? Yeah, that's chi. So I guess that would be sigma. Yeah. Okay.
Yeah, that's chi actually. So
yeah, but I imagine that's like sigma because right. Your y-axis is not normalized spectrum anyway, but that's why is it fluctuating like that?
Yeah, so the thing is the LAC-SPC background, I mean there's still some work to be done with the proper estimation of the LAC-SPC background, and this source was quite faint. So especially for region 3, we could not, I mean our background estimations was quite bad. So
the source was faint but hard.
I didn't catch that.
The source was faint but hard.
Yeah, faint but hard. Yes.
Okay, that's how you had that problem in the okay.
Yeah.
And all right, okay, so all right, that's what I was just a simple thing I was wondering if that affects the power law you're going to fit it. So
that's a very good
imagining if that you took that into consideration, that that the source is harder. So anyways, thank you. That was a simple question. Thanks.
Is there any other question? Ozan Toyran, yes, we listen you.
Hello, Neal. Can you hear me?
Yes, Ozan.
Yes, thank you for the nice talk, and so good to see you here. So my question is about your temporal analysis. Did you, did you see anything, or what did you look for?
Actually, we mentioned we had a section of temporal analysis in the paper. But, the referee asked us, I mean, he told us that there's nothing. I mean, the thing was, for region 2, we saw a temporal bump which could be fit with the Lorentzian. But apart from that, and even the norm of the Lorentzian was not that good. It was very less. So apart from that for regions 1 and 3, there was absolutely nothing. It was just Poisson noise.
I see.
So,
I see.
Yeah.
So the source was in the soft state when you found it. So
yes,
maybe
yes.
I thought maybe the RMS percentage would give you some clues about again the.
We did some RMS studies, but then again there was nothing significant in there. So,
I see. Okay.
Yeah. I mean, and but we did try to look for. We did try to look for. I mean, we did perform temporal studies, but since there was nothing significant, it did not end up in the research paper.
I understand. Okay, thank you.
Yeah.
Thanks for the answers. Is there any other question? Okay, then let me ask a question to you, Neal.
Yes,
actually, in your introduction of Astrosat, you told us SXT has the energy range from 0.3 to 8 kV.
Yes,
and
yes, yes.
Lux PC goes to 80 kV. But in your hardness evolution, you used up to 30 kV. And also in your Spectral, I see that it goes to 20 kV. So can we say that this is the most efficient way to use Astrosat data?
So it depends on the source actually. Our group has done a study of Cygnus X1, and in that we could, because the source was significantly brighter than this source, we could go up to 80 kV and perform both spectral and temporal studies till 80 kV. So it depends upon the source brightness, right? So how
Okay. And I have another question. So here in the slide that you show right now, T-BOPs and simple. Simple is for comptonization, to take into account comptonization. So there's a gamma factor there.
Yeah. There's a photon index factor.
Yeah. By the way, for the energy range, it must be always better to use higher energy range to take into account comptonization, because as we know, the effect of the comptonization starts at least after 15 kV in any way.
Right.
Yeah.
So because we used a simple model, we did the energies extend in XSpec. There is something called the energies extend, which basically extends the energy, even though your data is till 20 kV, it extends, it extrapolates and extends your data in certain log bins greater than, so greater than
that's okay, that's totally fine. But I just want to ask you, why did you choose simple maybe I missed that point, simple component instead of using some other comptonization components like CompTT or CompPS, etc.? There are few models to take into account comptonization.
We did try NTH comp and iReflect to look at the reflection features and all that. But the problem was that for NTH comp, the fits were not good, the residuals were too bad. And then for iReflect, the data, because it's a heavier model, the data was not good enough to do that. So we could not get the data to fit those models. But we did try. I mean, simple was not the first model that we tried. We did try other models too, but we ended up with simple because it gave us the best residuals, chi-square.
Okay, so can we say that in simple, gamma factor is related with the optical depth of the corona?
Yes.
Okay.
Yes, it is.
Okay, thank you again. So is there any question from the audience? If not, let's thank our speaker again. So we are very appreciated listening to your talk. So
thank you.
See you next Monday in our next meeting. Bye for now.
All right. Thank you very much for having me. Bye.